In consistent hashing, the main idea is that the keys and the nodes map to the same ID space. So what we're going to do is create a metric space, such as a ring, and we'll put nodes on this ring, and the idea is that these nodes each have some ID. Now the keys should also map to the ID space. So in this case, just for the sake of example, let's suppose that we have a 6-bit ID space. So IDs might range from 0 to 63. Now you can see that the nodes have IDs, and the keys also have IDs in the same space. A consistent hash function will assign the nodes and the keys an identifier in this space. A hash function, such as SHA-1, might be used to assign these identifiers. In the case of nodes, the ID might be a hash of the IP address. In the case of keys, the ID might simply just be the hash of a key. Both of these hash operations create IDs that are uniformly distributed in the ID space. The question now is how to map the key IDs to the node IDs so that we know which nodes are responsible for resolving the lookups for a particular key. The idea in Chord is that a key is stored at its successor, which is the node with the next highest ID. So for example, the key corresponding to the key ID of 60 would be stored at the node with the node ID of 1. Similarly, for the key with the key ID of 54. 42 would be stored at the node with the node ID of 43, 17 at the node with 32, 7 and 5 at the node with ID of 10, and so on. Consistent hashing offers the properties of load balance because all nodes receive roughly the same number of keys, and flexibility because when a node joins or leaves the network, only a fraction of the keys need to be moved to a different location. You can actually prove that this solution is optimal, meaning that the minimum number of keys need to be remapped to maintain load balance when a node joins or leaves the network.